Okay, so this week we're going to talk about 4.1 and 4.2. So 4.1 is exponential functions. So the definition of an exponential function is an exponential function f with base b is defined by the function f of x equals b to the x power, or y equals b to the x power, where b is a positive constant other than 1, meaning that b has to be greater than 0, and b cannot equal 1, and x is any real number. Okay, so the key thing is we're looking at this b value. We want to make sure that it falls true to be positive, it cannot equal 0, and it cannot equal 1. Okay, so determine if the following are exponentials. If not, explain why. So looking at A, f of x equals 2 to the x power. Since 2 is greater than 0 and 2 does not equal 1, then yes, this is exponential. Okay. And looking at B, we have g of x equals negative 1 to the x power. So since our b value equals negative 1, and we know that b has to be positive, the answer here is no. Because it has to be positive. Okay, looking at C, h of x equals 3 to the x plus 1 power. Here our b is 3, and that works out because it's positive and it doesn't equal 1. And then D, j of x equals 1 to the x power. Since b equals 1, that's going to be no, because we know that b cannot equal 1. Okay, so that's our key thing about exponential functions. We always have to be careful about what our base is. Okay, so the first thing we're going to look at is just evaluating an exponential function. So the exponential function f of x equals 42.2 times 1.56 to the x power models the average amount spent, f of x, in dollars at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 4 hours? So we know x equals 4. So if we plug that in, f of 4 equals 42.2 times 1.56 to the x power. Okay, oops, not x power, how about to the 4th power? Okay, so when you're plugging that in your calculator, remember to get that exponent, you're just going to use the caret. So if you type this in, you're going to do 42.2 times 1.56, then you're going to hit the caret 4. Okay, you can plug this all in at one time, and if you do that, you get the decimal 249.9, okay? And since it says to the nearest dollar, we can round that, and we get $250. And that's your answer. Okay, so one of the main things we want to look at in this unit is looking at the graphs of these. So we have 5 key graph aspects that we're going to use to help us graph. Alright, so the first one, if I can get this to move over. Sorry guys, hold on. There we go. Sorry about that. Okay, so the first one, we're going to look at domain and range. So our domain is always going to be negative infinity to positive infinity. There are no x values that we can't plug in. Okay. Then the range, we're never going to get a negative value. So our range is going to be from 0 to infinity. And at 0, it's going to be a parenthesis because we're never going to get the y value of 0. Okay. Then the graph, f of x equals b to the x power will always pass through the point 0, 1, okay, which happens to be our y-intercept. Okay, with that, we will have no x-intercepts. Okay, so that's one of the key points that we're always going to use the graph. Our just general function is going to be at 0, 1. With that, your book doesn't really talk about it, but we will also always have the point 1, comma b. Okay, that's just an easy one whenever we're making our table to see what our graph's going to look like. And we'll look at that in a few minutes. Okay, 3 and 4 kind of go together. So if b is greater than 1, then the graph increases. Meaning when we graph it, it's going to increase, go up from left to right. Okay. Number 4, if 0 is less than b, which is less than 1, then the graph decreases. Okay. All right, number 5, we have f of x equals b to the x power is 1 to 1. Meaning for every x value, it has only one y value, and for every y value, it only has one x value, which means it has an inverse. And that inverse is what we're going to look at here in a bit in 4.2. Okay, and then our last characteristic about the graph is that the graph approaches but does not touch the x-axis. So y equals 0 is the horizontal asymptote. Okay, and that's what makes that range go from 0 to infinity. Okay, so when we start graphing these, we're going to start looking at translations. When the graph is translated, the y-intercept and the horizontal asymptote will shift. Okay, sorry about that. My dog just woke up. Alright, so looking at the next page, we're going to review our translations real quick. So remember, vertical translations is when we're moving up and down. So if we're adding a value outside of our exponent, we're moving up. And if we're subtracting, we're moving down. Remember, horizontal translations are left and right, and those are always backwards. So if we have x plus c in the exponent, we're actually going to be moving to the left. And x minus c, we're going to move to the right. Okay. Reflections, if it's on the outside, that's going to shift, or not shift, sorry, how about reflect the x-axis. And one we don't see very often, but b to the negative x power, this reflects the y-axis. Vertical stretching or shrinking. So if c is greater than 1 and we're multiplying that on the outside, that's going to be a vertical stretch. And if it's a fraction, it's going to be a vertical shrink. Okay. Oh, sorry. Okay, and then if we're multiplying in the exponent, remember this is always backwards, so if c is greater than 1, this is a horizontal shrink. And if it's a fraction, it's going to be a horizontal stretch. All right. So with our graphs, we're going to use our parent function, f of x equals 3 to the x power, to obtain the graph g of x equals 3 to the x plus 1 power. So whenever you're graphing these, what I suggest you do is make a table. And we kind of talked about this in our characteristics. We talked about if we use 0, we always get the y-intercept of 1 for this general function, 3 to the x power. Okay. The easiest number to plug in after 0 is 1, and 3 to the first power equals 3. And then what I suggest you also use is a negative. So if I plug in -1, 3 to the negative first power, remember negative exponents make fractions, so we get 1/3. So if I go over to our graph, and we graph, let's see here, we have -1, 1/3, 0, 1, then 1, 3. And then the other thing we have to remember is that we are never going to cross this x-axis. So I'm going to go ahead and put our dashed line to represent our horizontal asymptote. And then you're going to make a swoop. Okay. And there you go. So that is our function for f of x. So now that we know that function, we can easily graph g of x. So g of x is f of x shifted 1 unit left. So what's nice is that horizontal asymptote isn't going to move, but each of our points will. So now our y-intercept is 3. And there you go. That's your graph of an exponential function. Okay. So now let's look at b. I'm going to actually change b a little bit. So you use the graph of f of x equals 2 to the x power. Let's change that so that way we see a decreasing function. Let's make this 1/2 to the x power. Okay, so start off with making your same general table. And again, I'm going to use -1, 0, and 1. Okay, so starting with 0, if we plug anything in, anything to the 0 power is 1, and anything to the first power is itself. Okay, now if we plug in -1, so 1/2 to the negative first power, remember negative exponent makes a fraction, and if we have a fraction, it flips it. So this becomes 2/1, or just 2. So, again, we have our horizontal axis, or asymptote, sorry, on the x-axis. We have the ordered pair -1, 2, 0, 1, and 1/2. Okay, so you can see based off those 3 points that our graph is decreasing now from left to right, which shows the difference between those base values. Okay. All right, so now if we want to graph g of x, is f of x shifted up 3. So everything's going to move up 3, and that includes this horizontal axis. Or sorry, asymptote. I keep saying that wrong. So if we shift that up 3, and then shift each of your points up 3 as well. And that will give you your new graph for g of x. And be careful again not to cross that asymptote. Okay, so with exponential functions, we have another function. Why is my screen not moving? There, okay. So, and that's called the natural base e. So e is an irrational number, and it appears as the base in many applied exponential functions. The number e is defined as the value that 1 plus 1 over n to the n power approaches as n gets larger and larger. So think about if you plugged in infinity. Some very extremely large number. So as n approaches infinity, the approximate value of e to 9 decimal places is this number here that I'm not going to read to you. Okay, so this irrational number e, we say is approximately 2.72, and we call it the natural base. So the function f of x equals e to the x power is called the natural exponential function. So this works the same as if we had base 2. So think of e as just being some number kind of like pi. So when you are looking at this and you're wanting to evaluate, like we're going to in this next example, when you're using your graphing calculator or any calculator, when you're looking for e, you're going to actually be looking for your natural log. So you're usually going to hit second or shift, depending on your calculator, ln. Okay. If you're using your Texas Instrument graphing calculator, that's going to be to the left of the 7. Okay. I'm going to show you really quick, actually. Okay, so here's a graphing calculator screen. So here to the left of the 7, we have a log, and just underneath it is the natural log. Okay, but if you were to hit second, hold on, let me clear it out. What did I just hit? Second natural log, you're going to get that e right there. And then any number you type in will go to the exponent. Okay, so that's one quick way to help you with the calculator. And we're going to come back to this in just a little bit. All right, so back to notes. So I'm going to kind of skip some of the sentences, but by 1960, the population of wolves was reduced to 800 wolves. The exponential function f of x equals 1,145 e to the 0.0325x power models the gray wolf population of western Great Lakes. F of x, and then x years after 1978. So according to the model, what was the gray wolf population rounded to the nearest whole number to the western Great Lakes in 2014? So we're going to find x first. So we're looking for the year 2014, but we started in the year 1978. So this was like year 0. So we want to figure out how many years have passed. So 2014 minus 1978 is 36. And then we're going to plug that into our function. And then it's just a matter of plugging it into your calculator. Okay, so I'm going to show you on that other calculator screen. So if we plug that in, we have 1,145, and then second ln to the 0.0325 times 36 power. And we get 3,689.18. And since it said approximate to the nearest wolf, that would just give us 3,689. And that's your answer. Okay, so one of the most common functions with e is interest, and any exponential actually. So compound interest, we have two different types, but either way, the basic rules of them are all kind of the same. So we're always looking at t in years. The balance a, okay, that's going to always represent your final amount. Okay, with the principal p. Okay, and principal is always going to be your starting amount. And then we have our annual interest rate R. Okay, and we're always going to write that in decimal form. Okay, so we have two formulas. The first one is if we're compounding so many times in a year. And then our second is if we compound continuously. And what I suggest you do for this compounding continuously, in my mind, continuous is going to represent when n equals infinity. Okay, and n is how many times are we compounding. So with that, if I say we're compounding monthly, that tells us that n equals 12. So if we say semi-annually, that tells us n equals 2, because it's twice a year. So you're thinking as how many times will that occur in a year. So we're going to do these two examples. So you decide to invest $8,000. So that's your starting amount. So that's our principal. For 6 years, that's your time. And you have a choice between two accounts. Your first account pays 7%, so our rate is 0.07, and it's compounded monthly, so that's your end value. Our second account pays 6.85%, so 0.0685. Oh, and that's your R. And it's compounded continuously, so I'm going to use infinity. So we're going to have two different formulas here, and we're going to figure out which ones are better investment. So our first one, A equals 8,000 times 1 plus 0.07 over 12 to the 12 times 6 power. Okay, so I just plugged into that first equation. Okay, here's the one thing to be careful about. Depending on your calculator, you're going to potentially have to put parentheses inside the parentheses with this fraction and also around your exponent. Okay, so when you're doing your homework, if you're getting it wrong, try adding more parentheses. If you're still getting it wrong, take a picture of what you're typing into your calculator and send it to me. Okay, but if you're checking with this, when you plug it in, you should get your value would be $12,160.84. And we're always going to round to the nearest cent unless it tells us otherwise. Okay. All right, for the second one, we have our rate, 0.0685, compounded continuously. So A equals our principal, 8,000, e to the 0.0685 times 6. Okay, compound continuously is easier to plug into the calculator. And if you do that, you should get $12,066.60. Okay, so on this one, let's see, it looks like the better investment is account 1. Okay, because that has the larger value. All right, so the last one, looking at this same thing. So a sum of $10,000 is invested at an annual rate of 8%. Find the balance in the account after 5 years, subject to A, quarterly compounding, and B, continuous compounding. So a sum of 10,000, so that's our principal, at an annual rate of 8%. Five years is our T. So the only thing that's changing here is our compounding. So our first account, or A, is quarterly. So N equals 4, because it's 4 times a year. So if we plug that in, we have A equals 10,000 times the quantity 1 plus our rate, 0.08, divided by N of 4, all to the 4 times 5 power. So if you plug that all in your calculator at once, you get approximately $14,859.47. And for the second account, part B, continuous compounding. So that means N equals infinity. So A equals 10,000, E to the 0.08 times 5 power. And that gives you the final value of $918.25. So on this one, it's actually better for the continuous compounding because they were done at the same rate, and so we want to be continuous.